Okay, so arithmetic in rings, we will just learn about some properties and some arithmetic inside the rings. We define the ring to be a set with two operations. One of them is denoted addition and the other is denoted multiplication, but they are not necessarily the addition and multiplication that we know. Okay, so an operation of addition inside the ring. So one may wonder, what's about the opposite of addition, subtraction? Because we have additive inverse in the ring. One may think about subtraction of elements. Can we do that? And we will deal with this in the following theorem. Okay, this theorem preloads for introduces the first step towards what I said about subtraction. So this says for any element A in the ring R, the equation has a unique solution. Actually, we know that every element in A has every element A in R has an additive inverse that we denoted minus A. It is a notation. It's not a negative sign. It is a notation for the additive inverse. So this equation says this theorem says this equation has a solution. We know that already because we know that a solution is x equals negative a, and that already belongs to R. But what this theorem adds is the uniqueness of that element. So this theorem will say that if you are given an element in a ring, then the additive inverse of that element in the ring is unique. So this talks about, in here, if you go down to the screen in here, this is the conclusion. Negative a is the unique element in the ring R such that a plus, this is the addition we know, that element which is denoted negative a gives 0 from both ways, from left and right or right and left. To make things clear and to help you not to keep imagining that the negative here is the negative that you know when you deal with numbers. No, it's not the case. For example, if we choose R to be Z7, okay? So what is negative 1 in there? We know it is 6, correct? So let me see, in this ring, we have negative 1 to be 6. So it's not about a negative image. No, it is the additive inverse. And we want to prove in this theorem this additive inverse is unique. How to prove something is unique, an object or an element is unique in mathematics? Assume there is another one who does the same job. So if V here is another solution for this, and see what happened now. Start with V, it is 0 plus V, but we can rewrite 0 as A plus U because we are assuming that we have U here to be the additive inverse, that we have it from R, this U. So we called that element U, and we assumed there's another element that does the same job, and we called it V. And we want to show now V and U are the same element. So we replaced the 0 with A plus U because A is negative, U is negative A. Now we will keep saying negative A, but we mean it is the additive inverse. Okay, it is not the negative image as I pointed out here. Okay, now from here to here we use associativity. We use the commutativity of addition because a ring is an abelian group under the addition. So I changed the places of U and V. Okay, now from here to here we use associativity of addition. So we add A plus V at the beginning, but we assumed V to be the another additive inverse of A, so that equals 0, and we got U plus 0, which is U. So we started with V equals all the way to U, and that means U is V, and so there is only one additive inverse for every element in the group, for every non-zero element in the group, and it is pointed out up there now in bold. So in here it says now this provides a meaning for a negative in any ring. So from now on we will say a negative a, but we don't mean a negative image, we mean the additive inverse. Okay, but instead of saying that always the additive inverse of a, the additive inverse of a, and repeating that, we will just say minus a. So it is a matter of notation. So I will emphasize that here. Minus a is the additive inverse of a, is the additive inverse. Good. Here again, this is our example. In Z6 we have negative 2 is 4. In Z14 negative 9 is 5. And in Z6 we have 1 minus 2. Okay, so now we can define subtraction between elements, but we don't mean literally another new operation. No, it is addition of the additive inverse of some element. So some element subtraction another element. It is that first element plus the additive inverse of that other element. As we see here, 1 minus 2 is 1 plus the additive inverse of 2. Well, and the additive inverse of 2 is 4, so we get 5. So interesting. So if you show this to somebody who is not taking algebra yet, he will get crazy. What? 1 minus 2 equals 5? Where are you living? And you tell him that I'm living in a system called Z6. So having fun in what happened in Z10. In Z10, 1 minus 2 equals 1 plus a negative inverse, negative 2, the additive inverse of 2. But this is 8, right? And we got 9. So 1 minus 2 is 9. That's in Z10. And 1 minus 2 is 5 in Z6. Okay, good. Now, in rings, we can do cancellation now. The thing that you are used to do a lot of times in many of your courses in school and in calculus courses and in real analysis. You were very comfortable to say if I have a plus b to equals a plus c, then I can cancel a and then I get b equals c. It was so easy. So why we are taking it as theorem here? Isn't that like kind of very intuitive, very basic? Why are we taking it as a theorem here? Because this is not an intuitive thing. It was intuitive thing for you when you used to work with numbers. Numbers were coming from Z or Q, the rationals, or R, the real numbers. And all of these are rings. So you can do cancellation for addition intuitively. But this is cannot happen in a system which is not a ring. But so far you did not deal with systems that are not ring to see where this might not be happening. Where this might not be happening. Maybe if some example comes to my mind now, to my brain, where this is not happening, what I need to make a subset which is not a ring, and actually here is not a group, where such cancellation will not happen. But that will take me away from my point. If you take the natural numbers and subtraction, now I don't want to confuse you here. The addition in the theorem represents an operation. Okay? We can take that operation to be, it's a binary operation, right? So we can define a binary operation of the naturals to be the negative, okay? Now, can we make counterexample for that theorem using operation subtraction? I mean, not a negative subtraction in n. Can we make some? I need to think about it. I will let you think about it. Make a system, a set with some binary operation where, according to that operation, cancellation that don't happen. Play with it. Maybe it exists in the exercises. We will see later. Okay. Let's keep going into the proof. We want to show that a plus b equals a plus c gives a equals c. So we're starting here. These are two equations. What we did, we added the negative image of a to both sides, and then we used associativity. But that gives 0, and this gives 0, and this is identity. We got b equals c. So this is so quick. Okay. But we will see later when we have it's not necessarily true that if we have multiplication, not a plus b equals a plus c. Here I'm saying a times b equals a times c. Would that give a b equals c? The question might be yes and might be no. And that may look strange for you because you used to work with numbers. Integers or rational numbers or real numbers, all of them were integral domains. So you did cancellation without any problem. But we cannot do so in general systems, not in any system. So we need to characterize in what system we can do such a cancellation, and we will see it today. Okay. So in not any ring we can do cancellation with multiplication, but with addition in any ring we can do the cancellation. So okay, now we will see a theorem that would look very silly for you, very intuitive. What are you telling me that a times 0 shall be 0, which is 0 times a, and 0 times 0 is 0? What, you want to show me that? I know this since first grader, but you know this for numbers. Now we are dealing with rings. We want to show it in rings in general. And also a times negative b. Remember, negative b is the additive inverse of b. If I multiply a with the additive inverse of b, would that be the same if I first multiply a and b, take the result and take the additive inverse of it? In either case I get the same result. This theorem says yes. Okay, but it looks to you that it is a multiplication of negative. They follow the same rules that you know for multiplication with signs, negative or positive. Same thing happening here. If the additive inverse of the first element is multiplied by the other element. Okay. 3. Negative times negative is negative, you know that. But here we are saying that if you take the additive inverse of some element and then you get a new element, take the additive inverse of that new element again, you get back to a. Oh, okay, all that needs to be proved. 4. It says, oh, okay, if I add two elements and then take the additive inverse. On the other side, I take the additive inverse of each element and add them. Would I get the same result? The answer is yes. This is number 5. Number 6 says, oh, okay, if I multiply the additive inverse of this one and that one, would that be the same as multiplying the two elements? So I have one element and two elements. First element, second. Take the additive inverse of the first, multiplied by the additive inverse of the second. That will be the same as if I multiply the two elements without their additive inverse, which means for you, negative times negative is positive. So there's almost nothing new for you here. What we need to prove them, huh? Because we are assuming we are doing this for general rings, not only the rings you used to work with, the real numbers, the rational. Okay. So let's prove the first one. So how they prove it? See, it is like I'm trying to convince you that we need to do these proofs. Okay. Okay. Now what will happen here? It shows this part equals that part. Okay. So these two parts are equal. What it will do next? It will say, okay, so I have something plus some other thing, and that something is coming back here again. So this element is repeated here. So by the theorem we just have seen, we can do cancellations for addition. So we are left with this part here equals that part. So a times 0 is 0. So this is the idea, and you can follow through that. Okay, let's go to the second part. In here, in the second part, we want to prove that, see, look at it very intuitively. A times b. Okay, a times b. I want to show that the inverse of this element is a times negative b. Okay? Huh. But did you see the word what I'm saying? I want to show that the inverse of AB is a times negative b, which means I want to show you that this is AB, right? Add to it this element, we get 0. from here to here. Correct? So AB added to some element, we get 0. So that some element is the inverse of AB. Correct? And we are done. And you can go through this using the distributive laws, because we are in a ring. Okay? Now in here, it wants to show that the inverse of this element, I have an element here which is minus A. What is its inverse? We are saying it is A. So what we will do to show that the inverse of minus A is A, I will take the minus A and add A to it, I get 0. So A is the inverse of minus A. Okay. Again, like what happened here, look. It will show you that the inverse of A plus B, so I'm adding A plus B and then I'm taking the inverse. I want to show you that it is the same as minus A plus minus B. So what I will do, I will add this element in red in here to that element. Okay, I will add this element to this element and get the result to be 0, which means the element whose this side is the inverse of that element in red, the left side. So I add them together now, keep using associativity, and you get all the way to 0, and then we are done. Okay. So I'm trying to convince you with something that you may look, which might look to you very silly, because you're still seeing these things as multiplication of negative signs. But I'm insisting here they are not negative signs. It is notation for additive inverse. Okay, let's keep going. We want to show here what we want to show. The inverse of A minus B is all that. Okay. So it's for you it is, oh wait a minute, why don't we do distribution and then we are done? Why we are doing all that effort? Doing distribution, that means you are dealing with it as a minus sign, and we are saying it is not a minus sign, it is a notation for additive inverse. Okay, so what we will do, we will write the negative B as we seen before, plus minus a negative B. Okay, and now here we are not doing distribution. We are not from here to here, we are not distributing the sign. We are using the result of 4, which says that the additive inverse of the addition of two elements is the addition of their additive inverse. So we get to that point, which comes out to be interpreted as distributing the negative sign. And then by 3, taking the inverse of B, we get here. Okay, so for these two, I will let you think about them if you can deal, and you must be able, I mean, to think about them the way we thought about the above there. And at the end, I will tell you not to worry for the remaining of the course, because I want you to feel comfortable with these things. Just remember these things as if they were multiplication of negative sign as you used to. But from now on, you know this is a notation only, and we are dealing with general systems of rings, and the ones you are used to that you are used to were just examples, easy examples of rings. The integers z, the q, the rational numbers, the real numbers. Okay, good. Now let's keep going for the notation. As a matter in here, this might not be very clear. A to power n, it means for us multiplying a with itself n times, and you know what that means again, in case of the typing is not clear. And in here, you know that all this exponentation, you know them now. Now you may ask, why are we doing this again? We know that since school. This is to emphasize that we will have the same things that you used to, but this time with general rings, not only numbers. But we have to emphasize it. Now when we say n times a, that means, you know, it's addition, and minus n times a, it's addition. So there are examples below here, but I want to emphasize something. Let's work in here in this example. Let's work inside Z10. Okay. What did I wanted to say now? Okay. So we are working inside Z10. So the elements here are 0, 1, 2 all the way to 9, right? What if I say 23 times 5? Would that make sense for you? You may say, stop. 23 is not in the system. 23 is not in Z10. I will tell you now, okay, you are right, but we are using notation here. I mean to add 5 to itself 23 times. Okay, this is what this notation says, n in here. So this n is just a natural number. So this n is a natural number, okay? But the element A is an element of the ring. So in here we are not making an operation between a natural number and an element in the ring. That does not make sense, because the ring, it comes with its own operation. The operation might be composition of functions, or multiplication of matrices, or addition and multiplication modulo some integer, modulo 5. So we will not multiply that with z. Z is n, natural number, because that's coming from different environment. So a matter here is not a multiplication, it is annotation. So if you make objection that a 23 is not in 10, I will say, okay, I'm not assuming we are doing multiplication inside Z10, but I'm using that to tell you that I want to add 5 to itself 23 times. Same thing if we go to matrices, and you already used to see that in matrices, like if we work in in M2 of real matrices, 2 by 2 matrices with real entries, right? And then you will have no problem seeing like 7 multiplied by -1, 3, 4, and 12. You have no problem with that, right? That means you will add this matrix to itself 7 times, or just multiply the 7 to inside the entries. But this thing here is not from the system. So it's not is a matter of notation, okay? Okay, let's see this example. Let A be a ring. Now A plus B square. You know that, how to do it, okay? All the way. So we get here, and then we stop. We don't do, oh, okay, this is A square plus 2AB plus B square. We don't do that. We don't know if it is true or not. Why? Because we don't know whether the ring is commutative. These two parts, A, B, B, A, they might be equal. If the ring is commutative, then they are equal. If the ring is not commutative, they might not be equal. So we cannot write them this way. Okay, now it says here, if it is commutative, then AB equals BA, then we can write them in this form. Okay. Now we have seen what a subring means. We defined a subring already, right? It has 4 conditions. So in the blue box here, we recall the conditions or the axioms that are needed for subring. So first we needed them addition to be closed under addition and closed under multiplication, and the additive identity is in S, and the additive inverse of every element stays in S. Okay, so this says if I have A in S, then negative A must also be in S, the additive inverse of A. Okay, so if these 4 axioms are satisfied, then we know that the subset S, it is not non-empty, of a ring R is called a subring, right? Now, what does this theorem tell us here? It says, okay, you know, we can summarize these 4 axioms with only 2. So when you are asked to show that a given subset is a subring, then just to prove these 2 conditions here, 1 and 2. And to be able to do so, we must show that these 2 conditions will guarantee for us the 4 axioms. Okay? Now, to prove, let's start with 2. Here is identical with condition 2. Okay, see, 2 in here, this part 2 guarantees condition 2 for us. So this condition 2 is done. Then we need to show condition 1 here, and 3 and 4. Okay. Now to show condition 3, now we want to prove that 0 belongs to us. Giving these two conditions, we want to show the 0 belongs to F. Let's see. C is not empty, S is not empty, so it has some element C, okay? So the first part in here, it says that if we have two elements in S, then their subtraction will be in S, okay? And I have already talked what that subtraction mean here. It's A added to the additive inverse of B. Okay, so and that applies for any two elements in S, not necessarily distinct. It might A and B might be the same element. So if we have C in here, then C minus C by condition 1 must stay there, but this gives 0. So C minus C is 0, and it is in S. So we proved 4. Now to prove 3, sorry. To prove 4, given an element A in S, we want to show that negative A is in S also. Okay, now we have proved 0 in S from here, right? We have proved 0 in S. And we are assuming that A is an element in S. So we have 0 and A elements in S. Now we use part 1, which is given here, which says their addition also must be in S. So their subtraction, sorry. So 0 minus A must be in S, and we know that it is the inverse of A, so we got part 4. Now to prove part 1, which means if we take two elements in S, then their addition must stay in S. But now, since B is in S, then by part 4, we know it is by part 4 we got in here, we know that the negative B is in S, which means the additive the additive inverse. So B is in S, so negative B is in S. So I have two elements, A and negative B in S. Okay, now I will use part 1 given here again and say A minus negative B must be in S using this part, but A minus negative B is A plus B. So A plus B is in S. So good. So using these two conditions here, using this condition along with this condition, we have showed that these four conditions are achieved. So when you are asked to prove that a given subset, non-empty subset, is a ring, just go ahead and prove that the two conditions highlighted by yellow are satisfied, and then we are done. Okay? Now let me see here, we will not be able to prove this theorem actually this way unless we proved the theorem we have seen already, that it deals with some manipulation or arithmetic concerning the negative sign, which is a notation for us for the additive identity. Okay. So another part of this section talks about units and zero divisors, and we have already talked about this when we worked with modular arithmetic. If I jump to here, you know that the units in Z15 are the elements inside Z15 that are relative prime with 15, and these are all of them here. Okay, and you know 2 times 8 is 1. The multiplicative inverse of 2 is 8, and the multiplicative inverse of 8 is 2. Okay, but we have seen this for specific rings that are of this form Zn, but we did not call them rings at that time because we don't till that time we did not define what rings means here. Okay, the units in Z are 1 and -1 because they are the only elements in Z that have multiplicative inverse according to multiplicative inverse. So okay, so the definition here says, in general, an element in a ring R is called unit if there exists U in R that multiplies A from both sides and give 1, and U will be denoted A inverse, and that means the multiplicative inverse of A. But once we write minus A, we mean the additive inverse of A that we have manipulated already. Now let's see example. What is every non-zero element in a field is a unit? Do you agree? Every non-zero element in a field is a unit, because how we define a field, or let's recall it. It is a commutative ring with identity such that every element in it, non-zero element, has a multiplicative inverse. So this is true since every non-zero element in a field has a multiplicative inverse, which means every element, a non-zero element, is a unit. Okay. Now let's go to rings of 2 by 2 matrices, and we may assume for this specific example here, assume this ring comes from 2 by 2 matrices with entries from the real numbers. So let me call this matrix capital A. Now the question, when this element, which is a matrix, is a unit, which means it has an inverse, which means invertible matrix. So A is a unit in, so let me call this ring to be R, in R, if it has a multiplicative inverse, which means invertible matrix, huh? So that means invertible matrix. And you know when such a matrix is invertible, and this is true, it is invertible if and only if the determinant is not 0. Okay, and now if you pay attention, in general, if R is a ring that we don't know is a ring, we don't know which ring, and A is an inverse, that belongs to the ring of 2 by 2 matrices with entries from R. We don't know what R is. It might be Z, it might be Z5, it might be the rational numbers, it might be Z10. Then A is a unit in M2R if and only if, I want somebody to tell me, if and only if
the determinant matrix is unit in R.
Thank you. Not the determinant matrix, the determinant you see. AD, see again, AD minus BC is, thank you, a unit in R. In R, the ring that is coming from here. And on this question, on this, a question on the first quiz was pasted on this thing, right? A unit in the ring R. So for instance, let me use this space. What about A equals, let me just write some numbers like this, 5. And this comes from M Need more space here. Where did I go? Let me watch for that. Okay, yeah, maybe 2 by 2, but we are coming from the 8. Is that invertible? Determinant A equals 2, 3 times 5 minus 2 times 8, and that will give us 15 minus 16, which is minus 1, and that will give us 7 in the 8, right? So A is invertible, or we will say here we are using a unit in M2 as the 8, and you know now A inverse equals what? 7 inverse 5 3 minus 4 minus 2, and then you compute it. 7 inverse is what in Z8? What is 7 inverse? 7. And you can compute the matrix. Okay? Okay. Good. So we know what does it mean for an element to be a unit. Okay, now definition. What the definition says? It's zero divisor. So above we defined the unit, and now we define a zero divisor. You already have seen these definitions when we worked with modular arithmetic, but now we repeating them for general rings, not only for the n. So a non-zero element in a ring, so A in a ring R, is called zero divisor, provided that there exists a non-zero element C such that A times C equals 0 or C times A equals 0. So it might multiply A to 0 from one side, maybe not from the other side. Some two matrices, if you multiply them in some order, they give you 0. Okay, but if you change the order, you may get something different. But still, because it happens at some order, the result was 0, we will say that each one of them is a zero divisor. Okay, so one of them, this says or, not and. So a non-zero element will be called a zero divisor if we find another element which is not 0, and multiplied by a, we get 0. So examples we have seen before, 2 and 3, they are zero divisor because of this in Z6. 4 and 9 in Z12, they are zero divisors. Okay, now notice here something we will see in a little while, that 2 times 3 equals 4 times 3 when we work in Z6, right? Because each of them will give us 0. But we cannot do cancellation. We cannot say, okay, so 2 times 3 equals 4 times 3, then we can do cancellation because 3 in here, then 3 in here, and then we obtain 2 equals 4, and this is a disaster. Okay, why did that happen? When there are zero divisor in some ring, then avoid the cancellation. You cannot do cancellation when there are zero divisor. But if we guarantee that there are no zero divisors, then we can do cancellation. Okay, and that will motivate us to define, motivate us for the definition of integral domains. Okay, and what I just said, it is in fact a theorem that we will prove in a while. So let's go for this example and see what it says. Oh, we have two matrices. Okay, two matrices in here. Let F be a field in F such that A. Okay, now, okay, you can easily find matrices, 2 by 2 matrices with real entries that you multiply and then you get 0. And none of these matrices is 0, right? You can do numbers, you can work with numbers. But what this example says, it gives you a family of such matrices, a lot of them. It tells you that if you choose matrices of that form with A times D minus B times C equals 0, then that matrix is a zero divisor. And it tells you why. Okay, it says, okay, this is the matrix we're talking about. Multiply it by this, you get 0. And from the other side, this is the matrix we're having in hand. Multiply it by this, you get 0. Actually, if you pay attention of what we are saying here, then this is nothing new to you. Remember when we worked with Zn, okay, elements there, we have a theorem which says if you take any non-zero element from Zn, then that element is either a unit or a zero divisor. It must be one of these, okay? And now in here, it tells you that this matrix, a matrix inside M2 F, now F can be real numbers, can be rational numbers, any field. We want to have F to be a field. It tells you if the determinant is 0, this is the determinant of the matrix, right? Determinant of the matrix A, assuming this is A. It tells you if the determinant is 0, then that matrix is zero divisor, because we multiplied by another matrix and gave 0, right? So now you can conclude that given any 2 by 2 matrix with entries from any field, then that matrix, the determinant of it, is either non-zero or 0. If it is non-zero, then the matrix is invertible. It is a unit. But if the determinant is 0, then the matrix is a zero divisor, and this example shows that. So given any matrix in there, 2 by 2 matrix with entries from rational numbers, or entries from real numbers, or from complex number, or from any field. Given any 2 by 2 matrix, it must be either a unit, invertible, or it is a zero divisor. And that applies for all matrices, not only 2 by 2 matrices. All square matrices, 3 by 3, 4 by 3, and so on. But to prove it is given a 4 by 4 matrix whose determinant is 0, and show it is a zero divisor, it would take more work than just the one we see in the screen. Okay, now integral domain contains no zero divisor. This is by definition. This is how we define integral domain. A commutative ring with identity, so that every non-zero element is not a zero divisor. A commutative ring with identity that contains no zero divisors. Okay, now again, this is another example to say now cancellation. If we cancel 2 from here, we get 4 equals 10. This is wrong. Then we cannot do cancellation here, because the cancellation may fail in rings that are not integral domains. This is what I said. We will prove now cancellation is valid in any integral domain. Now, because we are guaranteeing that there are no zero divisors, then we can do the cancellation. Okay, now to prove that, assume we have A times B equals A times C in the ring R, which is integral domain, and then we want to prove B equals C, and we are choosing A not to equal 0. So let us assume we are having this. That means AB minus AC equals 0, right? Now use the distribution law. That means A equal times B minus C equals 0. But we are in an integral domain, and this belongs to the integral domain R, and this element also belongs to the integral domain R. So we have 2 elements, and we multiply them, we get 0. But we are in integral domain, we have no zero divisors. Now, this will happen only if one of them is zeros, right? This element in here times this element in here, the result is 0. So either A is 0 or B minus C is 0. So let me write that, but we are in an integral domain. So there are no zero divisors. Thus, we must have either A equals 0 or minus B minus C equals 0. But we chose A to be non-zero, okay? For that, for this cancellation to happen. Otherwise, it has no meaning. But A is not 0. So we must conclude that B minus C is 0, and that gives us what we wanted after the cancellation, B equals C. So we could do cancellation inside integral domain. Okay, now this theorem says every field is an integral domain, and you must conclude that by your own, because we are saying like some intuitive thinking. If the element is when in some ring, elements were either zero divisors or unit, right? So if they are units, then they are not zero divisors. So okay, some rings we have seen again, some rings we have inside them that every element is either a zero divisor or a unit. Okay, so if it is a unit, then it is not a zero divisor. Now look at the theorem. It says every field is an integral domain. Take a field F. Every element in the field F is a unit, so it is not a zero divisor. Then we are done. So we got integral domain. Now let's prove that. Let F be a field. To prove it is integral domain, we need to prove it is a ring commutative with identity that has no zero divisors. But we have all this information almost. Then F is a commutative ring with unity, with the unity or identity. We call it in this book identity, I believe. I forgot. Identity. So it's commutative ring with identity. So the only axiom is left to show is there are no zero divisor. So want to show that F contains no zero divisors. And how we do it? The same as in the proof of the above theorem. Okay, in general, if you want to show that some element is not zero divisor, what do? You assume that there is another element which is not zero. So let's say we have an element A, we want to show is not a zero divisor. I will assume there is an element C which is not zero and multiply it by, okay, sorry, let me, I want to show A is not a zero divisor. I will assume there is an element C. I should not say zero, not zero, okay, because I want to show it is zero. I want to show if there is an element C and multiplies A into zero, then actually that element C was already zero. So that means it will never happen that A multiplied with a non-zero element and the result is zero. This will never happen. So let's show that. Let A be an element of F. So we want to show that a non-zero element is never a zero divisor, okay? Now, if there exists C belongs to F such that A times C equals 0, then what we get? Then consider I want to use A inverse because we are coming from F. Consider that A inverse belongs to F since F is a field. Okay, so inverse in there. Now we will use this and multiply both sides by A inverse. So I got A inverse times AC equals A inverse times 0. Okay, but now this gives, using the associativity, we get that, and we know any element times 0 is 0, and then we get the identity of F times C equals 0, and that gives C is 0. So what we have achieved that, as we assume there is an element C belongs to F that multiplies A to 0, and we showed this will never happen unless you multiply A by 0. That C was 0. This way you show A is a non-zero divisor. Okay, so let's go back to above theorem. It says the above theorem says if we got a field whatever, finite, infinite field, then it is integral domain. Question, is the opposite true? If you go back here, is it true? Answer is no. Why? There are, okay, let me go back. Can you tell me about an integral domain which is not a field? Somebody want to tell me? I want an example of integral domain. So let me, is an integral domain. Somebody tell me integral domain. Give me a ring which is integral domain, but not a field. Z, thank you, Rowan.
Z.
Thank
Integral.
you. Yes, Z is integral domain, and it is not a field. Thank you. So every field is integral domain. So R is a field, so it is integral domain. Rational numbers field is integral domain. ZP, where P is a prime, are fields, so every one of them is integral domain. The opposite is not true, and we have seen an example here in green. But if we have a finite integral domain, then it is a field. Finite integral domain, then for sure, see this word, finite integral domain, R, then it is a field. So let me emphasize that. Finite integral domain gives field. Okay? So let's prove that. How we prove? So let's call it R. Okay, R. Since R is an integral domain, let me write it this way, then R is a commutative ring with identity or unity. I believe we call it identity here. Okay. So let's recall what is a field. To prove something is a field, we need to prove three things. One, it is some ring, it is a field. Then we need to show it is commutative ring with identity, and A inverse belongs to the R for every element A in R except the 0. Correct? We have this already, and we have this already. So what's left, we want to show that every element non-zero, see, emphasize that, non-zero element A in R has a multiplicative inverse. A inverse belongs to R. Okay, this is what we want to show, and the idea here is clever, some kind of clever, and we want to use the hypothesis finite because we know without this integral domain might not be fields. So we want to get to use this hypothesis. So let us write since R is finite, then let's write the elements R to be A1, A2, all the way to AN. Okay, so those are the elements of the integral domain. One of them is the 0. We don't know which one. Okay, you know, let me write the 0. Let me write the 0 here. Okay, so now none of the AIs is a 0. Okay, but we know R is integral domain, so the identity is in there. So the identity of R is one of these elements. Okay, now We are choosing, we have in hand an element A in the ring R, right? Now we are done. If we find an element in those here that multiplies A and gives the result 1, then we'll be done. Now consider the following. What I will do, I will multiply the element, this element here, A, with the whole ring. So what I get? A times 0 is 0. Then I get A times A1, A times A2, and then I will keep going A times AN. Good? Now, pay attention to what's gonna happen. For a while, we want to do the following claim. Claim, what does it say? I will say if AI does not equal AJ, which means I does not equal J, because we are using this, assuming these elements are distinct, not repeating. Okay, so if I does not equal J, that means the element AI does not equal AJ, then A times what I will show here. Now I'm assuming AI does not equal AJ, so I will multiply A with each one of them, so I get A times AI, and then I claim also after multiplication we still have non-equality. Okay, so I am claiming that, and we will get used of that. Why? With some use that will be useful for us. So the proof is here. So let me make it here. Assume no. We will do it by contrapositive. Okay. So the proof of the green in here by contrapositive. That is, assume AAI equals AAJ. So AAI minus AAJ equals 0. Good. And this gives A times AI minus AJ equals 0. Oh, okay, but remember we are in an integral domain, and then we got a multiplication of two elements to be 0. One of them is A and the other is AI minus AJ. Okay? But we are in an integral domain. And A is assumed to be not 0 because we chose it to be not 0. A does not equal 0. So we must have that AI minus AJ to be 0. And that will force AI to equal AJ. Good? So we have the claim proved. Good? Now, how we use that claim? Now, look at it in here. This, by the claim, let me write, by the claim, okay, the map, let me say the map F, that goes from R to A times R, which is defined by F of any element small r equals AR, is 1-to-1. You agree? So it is 1-to-1, and it is also, okay, so it is 1-to-1, let's say. It is 1-to-1, and R is finite. AR is finite. Okay? Since, so let me say so, because I want to use this conclusion, which is F is 1-to-1. So the cardinality of R must be the same as the cardinality of A times R. You agree? The cardinality of R is the same as the cardinality of A times R. Because you know that already, if you have a 1-to-1 map from one set to the other, but the other set is contained in the first one, right? So to make it clear, we want to, so let me say, add that, because A times R is contained in R, right? Why A times R? Because A is multiplied by element of R. The result will stay in R because R is closed under multiplication. So AR is contained in R, and there is one-to-one map from R to AR. So these two sets have the same cardinality, but one of them is contained in the other. So that means, therefore, or thus, R is the same as AR. Oops, okay. R is the same as AR. But the identity of R belongs to the ring R. So because of this equality, the identity of R belongs to AR. And what does that mean? AR is the multiplication of the small a with all elements of the capital R. And that means there must be some element, small r, in the ring R such that A times R equals the identity. And so R inverse A is R inverse, and it belongs to the ring. So what we have shown that giving an element in the integral domain, the finite integral domain, a non-zero element, then we showed that there is an inverse of that element in that integral domain. Okay, and this is the whole proof.